Good morning. This week, both lectures are on composite refractories. This is the outline. So today we'll go over the background information. And I wanted to spend some time going over corrosion resistance and thermal shock resistance, some of the background theory, because that's what's important on the composite refractories. And we'll also this morning go over the components in these composites. And then on Wednesday, we'll go over these different systems. These are probably the most common composites. Um, the original composites were carbon infiltrated magnesia or dolomite for basic oxygen furnace applications. And then the true composites are listed here. These other four, magnesia carbon for basic oxygen furnaces and ladles, alumina, silicon carbide carbon for ladles, alumina carbon for slide gates, nozzles and shrouds, submerged entry nozzles and ladle shrouds, and then aluminum magnesia carbon for ladles. So we'll go over the materials on Wednesday. Today we'll just go over the background for these composites and the different components that make them up. So these are refractory oxide carbon composites. They're composed of a mixture of refractory oxides and non-oxide aggregates. And the matrix is some form of carbon. And in the matrix, there's antioxidation agents. So these are made to improve two properties: corrosion resistance and thermal shock resistance. So carbon has low wettability in terms of molten metals, molten slags, glasses. If the molten material doesn't wet the carbon, it can't react with it. So low wettability is essential for corrosion resistance. And then thermal shock resistance. These composites, because of the carbon matrix, have high thermal conductivity and low thermal expansion. And I mentioned that this combination prevents the buildup of thermal stresses. And these composites also have a high work of fracture. So it requires a lot of energy to propagate a crack through the materials. And they also have high hot strength because of the carbon matrix. So the low wettability of carbon by various liquids, liquid metals, liquid slags, glasses, that really increases the corrosion resistance. And the corrosion resistance is increased because you reduce the contact area between the refractory aggregates and the slags. And also, because of the antioxidation agents that are added, you have increased corrosion resistance by the development of continuous changes that take place in their refractory microstructure. Basically, in the matrix of these composites, the antioxidation agents are reacting and improving the corrosion resistance. And we'll see how that happens when we go over the different types of antioxidation agents. So we'll just look at wetting of a solid by a liquid. For any type of corrosion reaction to take place, wetting must occur. And wetting is defined by a contact angle. So if the contact angle theta is less than 90 or approaching 0, which is complete wetting, that's the condition you need for corrosion to take place. Some general rules. Wetting is most effective when the type of chemical bonding, whether it's ionic, covalent, or metallic, is the same in both the liquid and the solid. So liquid metals aren't very effective in wetting oxides or non-oxide refractories. And liquid oxides do not effectively wet most non-oxide refractories. So that's why carbon is very effective. in the matrix. So this is a typical Cecil drop type experiment, um, describing wetting of a solid by a liquid. And you have to look at the interfacial energies here. And there's three different energies to consider. Uh, the solid vapor, this is your refractory substrate, and this is your liquid drop labeled slag. So the solid vapor, the liquid vapor, and the solid liquid, those are three interfaces. And these interfacial energies, you could consider them as the energy necessary to create a unit area of new surface or interface. Surfaces and interfaces have higher energies than the bulk of the material because of unsatisfied chemical bonds. So here's an angle theta of this liquid drop on the refractory substrate. It's greater than 90, so anything greater than 90 is considered non-wetting. If the angle here is less than 90 for this condition, you see wetting starting to take place, and then this is complete wetting. Theta would equal 0 in that case. So you can represent the interfacial energies with vectors. So gamma SV is the solid vapor interface. Gamma SL is the solid liquid interface. And then gamma LV is the liquid vapor interface. And this is your angle theta between gamma SL and gamma LV. So if you sum the vectors in the x direction or this direction parallel to the surface of the substrate, you get an equation that looks like this. Gamma LV times the cosine of theta equals gamma SV minus gamma SL. Or if you put it in terms of just cosine theta, solve for cosine theta, gamma SV minus gamma SL over gamma LV. So this equation describes the contact angle theta in terms of these interfacial energies. All of these have typical units of ergs per square centimeter. So gamma SV again is solid vapor interfacial energy. Gamma SL is the solid liquid interfacial energy. And gamma LV is the liquid vapor interfacial energy. So when the angle theta is 0, complete wetting, the cosine of 0 is 1. And so 1 equals gamma SV minus gamma LV minus gamma SL, just solving this equation here. So gamma, so these different surface energies, you can take a spreading coefficient. So that's SLS. So this has to be a positive number for wetting to occur. So SLS must be positive for wetting to occur. That's the spreading coefficient. So for wetting to occur, just looking at this equation, gamma SV has to be greater than gamma LV and or gamma SV has to be greater than gamma SL. So either one of these conditions or both will give you a positive spreading coefficient. So this is what a non-wetting situation might look like. This is a silicate glass drop, actually several droplets on graphite flakes. So here's a drop of a silicate glass. It's spherical, and then it's sitting on a piece of graphite. And here's another graphite flake and another one and so on. But you can see how the glass is balling up because it doesn't wet the graphite. So this is what you want in a composite refractory, whether this is a glass or a slag or a metal, you want these spherical droplets to form. And that just prevents corrosion from taking place. There's a little bit of background on corrosion, a little bit of background on thermal shock, high thermal conductivity, low thermal expansion. I mentioned this on a few of the refractory materials that we went over. High work of fracture, so a situation where it's difficult to propagate a crack. It takes a lot of energy to propagate a crack to keep it moving. High strength, low Young's elastic modulus. All of these, because of the carbon present, increase the thermal shock resistance. So the improvements in thermal properties, you have increased thermal conductivity because carbon and graphite has high thermal conductivity, and you have decreased thermal expansion due to the presence of carbon. The graphite flakes, because of the anisotropy and the thermal expansion, have microcracks present. So when microcracks close, they also decrease the thermal expansion. So the improvements in mechanical properties, I mentioned work of fracture. That's the energy necessary to propagate a crack. So it takes more energy to propagate a crack when you have microcracking, sliding of components, pull out of components, crack branching, and then bridging in the crack wake due to carbon flakes. So it takes more energy to drive a crack, and that's what you want to having improved thermal shock resistance. It doesn't take a lot of energy in a refractory microstructure, which is really a defect microstructure with microcracks. It doesn't take a lot of energy to start a crack moving, but you want to prevent it from growing by making sure you have high work of fracture, making it difficult to propagate a crack once it's initiated. These materials have high hot strength. Carbon has good hot strength, but you also have these antioxidation agents. Mostly they're metallic particles, and they can also improve the hot strength when they react with gases like oxygen. And I'll go over that in a few minutes. And a decreased Young's elastic modulus prevents stress buildup, and that's primarily because of the microcracks present. The microcracks will lower the elastic properties. So high thermal conductivity is desirable, low thermal expansion, high work of fracture, high strength, and low elastic modulus. That's what you want to build into the composite. So there's two approaches to designing a composite with improved thermal shock resistance. There's the thermoelastic theory and the damage resistance theory. The thermoelastic theory doesn't really apply to refractories. It really applies to advanced structural ceramics. This theory, you're designing a material to resist crack initiation. You don't want a crack to even start. In the damage resistance approach, you want material to resist crack propagation. So this is the one you want to use to design a refractory microstructure. So we'll go over both of these. So in the thermoelastic theory, that's simply resisting crack initiation. You don't want to even start a crack moving, and you're avoiding complete catastrophic failure. You don't want any crack growth. You want to maintain high strength when you thermally shock the material. So there's two parameters, and there's a series of R parameters that describe thermal shock behavior. The first is for rapid cooling. That's an R parameter. So this would be a very rapid uh, thermal shock situation. And then more, more gradual um, situation is where you have gradual cooling. This would be a less severe thermal shock. And R prime is the parameter that describes that. So R is the thermal shock parameter for a very severe or rapid thermal shock. You might be dropping a sample into an ice bath. Would be very severe thermal shock. And this equation is set up for a plate, an infinite plate. So R equals the fracture strength, sigma F, 1 minus nu, which is Poisson's ratio, and that's divided by A, which is the thermal expansion coefficient, and E, the Young's elastic modulus. It turns out that R just equals delta T at fracture. So delta TF is the temperature difference at fracture. So the experiment might be you take a sample that's sitting at a certain temperature, you drop it into a water bath or an ice bath, and you keep increasing the temperature of the sample. So the delta T is the difference in temperature between the sample and the, let's say, the quenching medium, an ice bath. And these parameters you can use to calculate delta T. So the higher the R value, the higher the delta T, the more resistance you have to a catastrophic failure. So high strength, low thermal expansion, and low elastic modulus. Typically, if you make a material that has very high strength, you're also going to have high elastic modulus. So that is sort of an issue in this equation here. The more you increase the strength, you're also going to increase the E. So they're going to kind of work against each other to make a high R value. What's really important is trying to make a really low thermal expansion material. So high R values, you need high strength, low thermal expansion, and low modulus. But again, it's not always easy to make a high strength material with a low elastic modulus. They usually go together. So here's a simple example, a soda lime silica glass versus a fused silica glass. They both have about the same elastic modulus, 10 times 10 to the 6 psi, so 10 million psi. The soda lime silica glass is about 10,000 psi for the strength. The fused silica glass is a little stronger, maybe 15,000 psi. Poisson's ratio nu is 0.2 for each one. Poisson's ratio for ceramics and refractories is usually about 0.15 to about 0.3. The entire range for nu is 0 to 0.5. So 0.2 is a typical value for Poisson's ratio. The big difference here is the thermal expansion coefficient, 10 times 10 to the minus 6 per degree C for a soda lime silica glass. This is pretty typical for a lot of refractories in that range also. And then the fused silica glass I mentioned has the low thermal expansion coefficient. It's 1/20th of the soda lime silica glass. It's only 0.5 times 10 to the minus 6 per degree C. So if you put these variables into this equation, you get a delta T or an R value of only 80 degrees C for soda lime silica glass. So you only need a temperature difference of 80 degrees C to fracture this glass. It's very brittle. The fused silica glass, because of the low thermal expansion, when you calculate delta T and R, is 2,400 degrees C. Obviously, this is above the melting range of a fused silica glass, but it just shows you the big difference in the R value because of this low thermal expansion coefficient. So this is a material that you can shock without fracturing it. The other R parameter in the thermoelastic theory is R prime. It's for a gradual quench. So we start out again with a plate, an infinite plate. So our delta T for fracture. Some of this equation is the same. Sigma F1 minus nu over alpha A E. We have a term here, K, the thermal conductivity. And then we have something related to the sample size. So 1 over 0.31 RM. RM is related to the sample size, half the thickness of this particular plate. And H is the surface heat transfer coefficient. So you can see in the denominator, the sample size makes the bigger the sample, the smaller the delta T. And the conductivity, the higher the conductivity, the higher the delta T. So for this infinite plate, we have this equation, and R prime is defined by the first part of this equation, K, the thermal conductivity times sigma F, the fracture strength, 1 minus nu, the Poisson's ratio, divided by A, the thermal expansion coefficient, and E, the Young's modulus. So if we want a high R prime value to resist crack initiation and catastrophic failure, we need high conductivity, high strength, low thermal expansion, and low Young's elastic modulus. So the thermoelastic theory, again, is designed for materials that we would call high strength, high performance technical ceramics. These would be fine grain size materials, low porosity, that gives rise, fine grain size, low porosity gives rise to high strength. And R and R prime are designed to prevent any type of structural damage, so that you don't want any drop in strength when you quench the material. So that's the thermoelastic theory. The theory that's used for refractories is a damage resistance theory. And here you're resisting crack growth. In the thermoelastic theory, you're resisting crack initiation. Unfortunately, in this theory, the thermoelastic theory, when you initiate a crack, it's usually catastrophic. In the damage resistance theory, you allow cracks to initiate. You actually start out with a microstructure that's highly microcracked, but you want to have a situation where the crack propagation is difficult. So you're allowing damage to take place in a refractory microstructure, but you're minimizing that damage. It doesn't matter how much strength you lose as long as the refractory is still intact. So both of these parameters, R4 prime and RST, are for rapid cooling. They're just starting with different crack sizes. So R4 prime is known as the thermal shock damage resistance parameter. So gamma F is the work of fracture times E, Young's elastic modulus, and now it's divided by the fracture strength squared, and 1 minus 2 times nu, the Poisson's ratio. So if you want a high R4 prime value, you need a material that has a high work of fracture, high elastic modulus, and low strength. Refractories are typically low strength compared to technical ceramics. So the key here is the work of fracture. You want to design a microstructure that when a crack starts moving through it, like from thermal shock, it is very difficult to move that crack. You want to dissipate that energy. The other parameter, RST, is the thermal stress crack stability parameter. So gamma F is again in the numerator, the work of fracture surface energy. and that's divided by the thermal expansion coefficient squared times Young's modulus, and that's the square root of both of these parameters. So for a high RST value, again, you need a high work of fracture. That's the key here. Low modulus and low thermal expansion. So we can look at R4 prime, and RST, and make a plot of strength versus a temperature difference, the delta T. That's the delta T of quenching. So these are a rapid quench situation, and we're starting out with a material with small crack size. So there's some initial strength SO, and then as we increase this delta T, we reach a delta TC, which is the critical temperature difference for fracture to take place. So that's described by R. We have a delta T described by R, and we have an instantaneous decrease in strength. Then R4 prime takes over in this region here. There's no change in strength, but when we reach another delta T that's critical, delta T critical prime, we then have a gradual strength loss taking place. That's RST in this region. So ideally, in a refractory material, we don't want to see this decrease in strength. We can really ignore the R parameter, and R4 prime and RST, we really want this gradual strength loss curve to shift up to this point here, so that we just have a gradual strength loss as we increase the thermal shock severity, that we increase the delta T. So if we compare R4 prime and RST, R is proportional to the strength over the modulus. R4 prime and RST is proportional to the modulus over the strength squared. So these are opposites. So what this tells us, you can't design a material to resist crack initiation and crack propagation at the same time. So you cannot maximize both the resistance to fracture initiation and crack propagation. So this is what we want for refractories, R4 prime and RST, E over sigma F squared. So this is an actual experiment, strength versus this quench temperature. And there's 4 different graphs here, and they're graphs for a material made with different grain sizes. So the bottom curve here is the smallest grain size, 10 microns. That might be typical for an advanced technical ceramic. High strength may be greater than 100,000 PSI. You start at a strength here, and this is in KSI, maybe just under 50 KSI. And then around 200 degrees, you have this rapid decrease in strength. The other graph on the top here is a larger grain size, 85 microns. That's more typical of a refractory, usually less than 10,000 PSI. So this one starts out at a lower strength, maybe a little more than 20 KSI. And then as soon as you reach this critical temperature difference, you have this gradual strength and loss, a gradual loss in strength. So this is what you want to see for a refractory material. You want to design a microstructure that allows a gradual loss in strength. You don't want to have a catastrophic failure in a refractory. So you can see the shape of these curves. It looks very much like this curve here, which is predicted by theory. So either R4 prime, RST, those theories work, and experiments like this prove it out. So those are very valuable parameters to design materials for thermal shock resistance. So in designing a refractory, um, greater flaw size, greater crack size, you have large grain size aggregates. So most refractories have uh, grain sizes on the order of a quarter inch, some quite larger. Greater number of cracks or flaws, so you introduce inhomogeneities in the microstructure. Porosity is important, and microcracks. So refractories tend to have large grain size, uh, high pore concentration, and a high microcrack density. So the thermal expansion coefficient A was in the denominator of these critical temperature difference equations, R4 prime and RST. So if you have material with zero thermal expansion coefficient, you're never going to develop a stress when you change the temperature. This is ideal, but unfortunately, all refractory materials have a certain finite thermal expansion. So the next best thing is a low thermal expansion coefficient. So you'll develop low stress levels as you change the temperature. And if you have a high thermal expansion coefficient, you're going to have your high levels of stress when you change the temperature. So this is thermal expansion versus temperature for some simple oxides. And I mentioned that MgO is one of the refractory materials that have the highest thermal expansion coefficient. So MgO and CaO are both up here, so is Fe2O3. So they're high thermal expansion. On this graph is amorphous or vitreous silica, fused silica. You can see how low that thermal expansion is relative to these refractory materials like MgO and CaO. The graph stops at about 900 degrees C because when you get higher than this temperature, especially at 1200 degrees C, this material crystallizes into cristobalite. Here's quartz, low to high quartz displacive transformation is shown. So that's a high thermal expansion material. And then alumina is a little bit lower than MgO. Chrome is a little bit lower than alumina, chrome oxide. And zirconia is a little bit lower than alumina. So those are expansions for simple oxides. None of them are really that low. Some of the binary and ternary oxides are shown here. This is the same scale here, expansion versus temperature. Here's a dicalcium silicate. Here's a spinel structure. Here's the magnesium silicate phosphorite, and here's magnesium titanate. They're also pretty high. Here's your spinel, MgAl2O4, and here's a spinel with a chrome addition. Here's zircon, it's starting to go down. And then here's mullite, Al6Si2O13. It's pretty low. So mullite has pretty good thermal shock resistance. And then this is a cordierite structure. It's pretty low, but again, it's not a high temperature refractory material. So mullite has advantages, and so does zircon for thermal shock resistance. And this is the curve for the non-oxides. Same scale, percent expansion versus temperature. And here's titanium carbide, boron carbide. Here's silicon carbide, which is boron nitride down here. So these are a little bit lower. And then at the bottom here, you have graphite and amorphous carbon. So this is graphite perpendicular to the basal plane. This is graphite parallel to the basal plane. So you can see how these graphites or amorphous carbon have advantages in low thermal expansion. And the fracture surface energy, this gamma F term, is in the numerator of R4 prime and RST. So there's various fracture surface energies. This one is a thermodynamic surface energy, and that's simply the energy necessary to create a unit area of new surface. So again, the surface has excess energy compared to the bulk because of the um, unsatisfied bonds at the surface. So gamma F, this fracture surface energy for crack propagation in a refractory, is not the thermodynamic surface energy, which is pretty low, 0.1 joules per meter squared. Gamma NBT, NBT means notch beam technique. That's not the fracture surface energy for crack propagation. It's the energy necessary to initiate a crack. And basically, it's the energy necessary to start a crack. So gamma NBT is low in refractory materials because of the high porosity and high microcrack density. That's about 10 joules per meter squared. So it's very easy in a refractory material because of the defects to start a crack moving. So the gamma F that we're interested in is gamma WF for work of fracture. So that's the effective surface energy. It's the energy necessary to propagate a crack. So that crack is going to interact with the microstructure. So gamma WF accounts for crack microstructure interactions, and it's much higher, 80 to 120 joules per meter squared. That'd be at room temperature. It even gets higher at higher temperatures. So what's causing a high work of fracture? There's frontal and wake process zones. I'll show you those in a minute. But in the frontal process zone, you have microcrack extension that dissipates energy, increases this gamma WF. You have crack branching, crack deflection, also in the frontal process zone. At high temperatures, you can have plastic deformation in the frontal process zone. And behind the crack, in the crack wake, behind the crack tip, you have crack branching. So all of these mechanisms make it difficult to propagate a crack in a refractory microstructure. So the higher the work of fracture, the more thermal shock resistant the material. Now, if you're talking about a very brittle material like a glass or a single crystal, gamma F, the thermodynamic surface energy, gamma NBT, the energy to initiate a crack, and gamma WF, the energy to propagate a crack, are all the same. So the energies for crack initiation and propagation are virtually the same in a glass and a single crystal. But in a refractory material, you design a microstructure for a high work of fracture. So this is what the crack process zones look like. This is the surface of the material, and this is a crack at the surface. So the crack is moving from left to right as it propagates. So this dotted vertical line represents the division between the frontal process zone and the wake process zone. So at the crack tip, it's an area of high stress concentration. So you're forming microcracks. They may be pre-existing, and you get all this crack branching taking place. So all of these surfaces that are created, all of these crack surfaces dissipate energy. And then in the wake region behind the crack, you have these coarse aggregates that bridge the crack. At high temperatures, you have a viscous silicate liquid that flows and bridges the crack. And CMOD is a crack mouth opening displacement. That's the crack width. So when you design a microstructure to be thermally shock resistant, you want a high ratio gamma WF over gamma NBT. Both of these are easily measured in the lab. So you can make a refractory microstructure and measure the energy required to propagate a crack or initiate a crack. So a material that's thermal shock resistance will have a ratio greater than 10. So you have high energy consumption during crack propagation relative to crack initiation. Basically, you have a refractory material that has microcracks and pores present. Those are your flaws. So the higher the ratio, the better the thermal shock resistance. And a refractory accommodates extensive internal cracking processes, but it still retains its mechanical integrity. So when you design a refractory, you design it to fail gradually. You really want to avoid any kind of catastrophic failure. So when this crack is moving from left to right, um, this frontal process zone reaches a steady state and moves along with the crack tip. So it has a certain stress field, and that basically the size of the frontal process zone remains constant and moves from left to right as the crack propagates. In the wake region, um, as the crack is moving from left to right, you have a constant size frontal process zone, but the wake region gets bigger and bigger as the crack extends. So both of these regions are important, the frontal process zone, but the wake and the wake region, but the wake region is more important because it grows in size and you design a microstructure to um, include mechanisms like aggregate bridging and aggregate pull out and perhaps silicate bridging at high temperatures. So the wake region is the most important because it dissipates the most energy. And then the crack mouth opening displacement. This width of the crack, if it's a brittle ceramic, a high performance technical ceramic, that's going to be very small, but it's going to be very large in refractory materials, and you need aggregates that are large enough to bridge that crack. So aggregate bridging is important, and I've listed 3 different mechanisms for aggregate bridging. Your aggregates obviously have to be stronger than the matrix, so the aggregates bridge in the wake across the fracture surfaces. They can wedge in the wake region also. And then when those aggregates are pooling out, there's frictional effects, and aggregates that are pooling out also dissipate energy. Silicate bridging only occurs at elevated temperatures. When you have a silicate glass that forms, it has to be a viscous glass. It flows and forms these bonding ligaments across the fracture surfaces. And that's only active over a limited temperature range. Once the temperature becomes high, very high, the viscosity decreases and the bonding ligaments disappear. So if you're going to have a silicate glass present, it should be a very viscous material. So how do you improve thermal shock resistance? What are the opportunities for improving crack growth resistance by controlling the microstructure, designing a microstructure? Uh, Actually, the 6th course in this lecture series is just on microstructural design for thermal shock resistance. Aggregate size. So aggregates have to be larger than the width of the crack mouth opening displacement. The aggregate geometry, you really want angular aggregates. They have better interlocking than a spherical type aggregate. So rough surfaces interlock better. Um, Obviously, you can add fiber additions. So they have large aspect ratios, like the diameter. They can bridge cracks. metal fibers are added in castable type refractories to improve the thermal shock resistance. The aggregate strength, the aggregates have to be stronger than the matrix. The aggregate surface texture, a rough surface is better than a smooth surface. And chemical bonding between the matrix and the aggregates. This is kind of tricky. You don't want strong bonding between the aggregates and the matrix. That's going to deactivate these bridging mechanisms. So you need a bond strength that's not that strong because you want to activate like aggregate pull out and frictional mechanisms. So if you make the bonding between the matrix and the aggregate too strong, you're not going to have a material that resists crack propagation. The cracks are just going to go pretty much straight through the material without going around the coarse aggregates. So that's some background on thermal shock and corrosion. So with that in mind, that's how these composites are designed. So the major components are oxide, non-oxide aggregates, and the chemistry is determined by the application. So whatever is compatible with the environment for that particular application, that's how you choose your coarser aggregates. They're going to influence the corrosion resistance, the thermal shock resistance, and the strength. The matrix is going to be carbon, perhaps graphite. This lowers the thermal expansion, increases the thermal conductivity. Because of the non-wetting nature, it improves the corrosion resistance. And you have an overall increase in thermal shock resistance and strength. You have to have antioxidants. These are protecting the carbon. Carbon, we mentioned, oxidizes quite easily. So you're adding something to reduce carbon oxidation, but this also improves the strength and corrosion resistance. And you have to have a binder. It ensures cohesion of all of these components. It allows for the material to be formed, but the binders also add additional carbon to the matrix. So the oxide or non-oxide aggregates, in terms of corrosion resistance, they have to be compatible if it's in contact with a slag or a metal or a glass. So you want to minimize the dissolution of the aggregates. So the aggregates by themselves, you want to have corrosion resistance. So you usually go with a high purity material that minimizes these impurity phases that develop at the grain boundaries. You want low porosity, and the fused cast aggregates have the low porosity for corrosion resistance. So you're minimizing surface area and large crystal size. That minimizes grain boundaries. And the grain boundary is the weakest area in the aggregates. That's where the corrosion takes place first. So high purity, large crystal size, low porosity for the aggregates. Large irregular aggregate shapes are going to increase the thermal shock resistance. It's going to create a more tortuous fracture path. Unfortunately, when you add large aggregates and porosity, that's going to decrease the strength. The carbon is there to provide corrosion resistance. Slags and metals do not wet carbon very well. It has low thermal expansion. I showed the graph of thermal expansion versus temperature. Graphite is anisotropic, so it develops microcracks. These cracks close when the material is heated. That actually lowers the thermal expansion. The carbon has high thermal conductivity. It also has good hot strength. Because of the anisotropic behavior and the microcracks, it also has high work of fracture. So the carbon provides good thermal shock resistance because of low thermal expansion, high thermal conductivity, and the high work of fracture. Oxidation resistance is not good for carbon. So decarburization increases the porosity, decreases the strength, and once you remove the carbon, the corrosion resistance decreases. So carbon oxidation takes place by a couple of mechanisms: direct oxidation of carbon by oxygen in the atmosphere, and indirect oxidation of carbon by different oxides. So this is why we have antioxidation agents to improve the oxidation resistance of carbon. But here's the case of direct oxidation of carbon by oxygen. So carbon plus oxygen gas forms CO gas. That takes place at temperatures usually less than 1,000 degrees C. So carbon plus oxygen can also form CO2 gas. So carbon plus CO2 gas can also form CO gas, and that dominates at higher temperatures about over 1,000 degrees C. So carbon removal or decarburization starts at temperatures as low as 400 degrees C, and it doesn't take a lot of oxygen. Oxygen partial pressures um, as low as 10 to the minus 5 atmospheres can cause oxidation issues. And then you can also have indirect oxidation of carbon by various oxides. So Me is an oxide, a metal ion in the oxide, MExOY. Me could be Mg. Mg is plus 2, oxygen is minus 2. So MgO could be a possibility. Could be Al plus 3 for Al2O3. But your metal cation plus in the oxide form plus carbon forms carbon monoxide plus the metallic form of the uh, metal. So any of these ions, Mg, Al, Zr, Si, Mn, Ti, Fe, and AK, will react with carbon, form carbon monoxide plus the metal. And that's basically how like iron oxide is reduced to iron. In a blast furnace, you just add carbon to the oxide and you form the metallic form of iron. But it also um, removes carbon from these composites. The antioxidants, they're there to reduce carbon oxidation. They improve strength and they improve corrosion resistance. So these are typical antioxidation agents: aluminum, magnesium, silicon, and then an alloy aluminum magnesium and another alloy aluminum silicon. TiO2 can also be used, silicon carbide can be used, and boron carbide, B4C. So the whole idea is that it traps the oxygen before it can react with the carbon, prevents carbon from oxidizing, and maintains the composite. They simply form uh, compounds that block the pores. They can also form a ceramic bond. So they trap the oxygen, form compounds that fill the pores and block further oxidation, and they can also form a ceramic bond, which would increase the strength. So this would be aluminum metal. It's usually added 2 to 5 weight%. So at temperature, liquid aluminum plus oxygen forms Al2O3, or you can also have this reaction: a liquid aluminum plus CO, carbon monoxide, forms Al2O3 plus carbon. So it's removing oxygen and carbon monoxide, and it's forming alumina and carbon in the pores. So that formation of these compounds improves the strength and corrosion resistance and decreases the porosity. So you're removing O2 and CO gas, and you're improving the strength. Silicon metal is usually added 2 to 5 weight percent. So Si plus O2 forms SiO2. Si plus carbon can form silicon carbide. And the silicon carbide can react with the carbon monoxide to form SiO2 and more carbon. So you can form silica, silicon carbide, and carbon. So any of these reactions are removing oxygen and CO gas, and they're forming a product that provides high temperature strength, is blocking the pores, and basically it forms a denser layer. It inhibits oxidation by forming this denser protective layer. That's the idea behind all of these antioxidation agents. Silicon carbide might be added by about 5 weight percent. So silicon carbide plus carbon monoxide forms silica and carbon. Silicon carbide plus CO can also form SiO gas plus carbon, and that SiO gas can react with oxygen to form more SiO2. So here you're forming silica and carbon. Again, you're removing the oxygen and carbon monoxide from the gas and forming compounds that fill the pores and provide a further protective layer by providing an oxidation barrier. Boron carbide, maybe 1 to 3 weight percent is added. So B4C plus carbon monoxide forms B2O3, which is a liquid plus additional carbon. So it's removing CO, and now it's forming a liquid phase which coats the carbon and forms an oxidation barrier. So the liquid is desirable because it can coat the carbon in the matrix, provide an oxidation barrier. But since you're forming a liquid, you're also reducing the hot strength. So that's one disadvantage of adding B4C, is this liquid is a low viscosity liquid, and it's going to reduce the hot strength. And then the binders, they're necessary to form these components. The composites can be pressed, they can be extruded. So you need a binding agent. So they provide cohesion. They also provide formability. And when they're pyrolyzed, they form additional carbon. So what's mostly used now is phenolic resins. They have a 50 to 70 weight percent carbon yield when they're pyrolyzed. Pitch has about a 50% carbon yield. So pitch, when these composites were first made, was widely used, but the phenolic resins are easier to work with. They have a little better carbon yield, and they're not hazardous. The pitch can have issues related to cancer. So I would say the phenolic resins have replaced pitch to a large extent. So again, a phenolic resin, 50 to 70 weight percent carbon yield. There's two types of resins, a Novolac and a Resol. They're both thermal setting. This Novolac requires a curing agent, hexamethylene tetramine. So they provide the formability and the bonding. They have to be cured about 250 degrees C. And this is what results. You have a methylene bridge, a CH2. They're bridging these phenol rings, which are C6H5OH. So these carbon rings are bridged by methylene. So there's a high carbon yield when these are pyrolyzed. Okay, I'd like to stop there And next time we'll go over all the different kinds of composite compositions. And we'll start with the historical, which ones were first made, and then we'll go describe all the ones that are currently made. So I think we'll stop there, and we'll finish up on Wednesday with all the different compositions of the composites and where they're used and how they're made. So thanks again for listening in today, and I'll see you on Wednesday.